so what I want to do today is to talk with you about why should we build a quantum computer, what would we use it for, how would we program it, and I want to discuss some of the myths around quantum computers, debunk some of them to help you kind of see what a quantum computer can really do and what may be a bit hard. And so just to set the stage before we start a conversation, I want to show some slide I have from the Paul Messina. He's the director of science in Argonne. So he builds large classical computers. And he had the panel a few years ago with the title enabling technologies for beyond exascale computing. Over the past 40 years, the speed of the fastest the supercomputer has doubled every year, meaning every 10 years the top speed goes faster by a factor of 1,000. Gigaflop, teraflop, petaflop, soon exaflop. But Moore's law is coming to an end, and so the question is, what can we do to go beyond exascale computing? And with that, he clarified then, and I think that's the key for our discussion. He clarified that he's not just referring to go to beyond 10 to the 21 floating point operators per second. But he was looking for something else. That is not just another factor 1,000 faster, but something that really fundamentally changes the way we compute. So when we think about quantum computing, and if I have a discussion, is that quantum computer faster than my laptop or not? That just misses the point. I really want something that's just so obvious that I want to have a device that can compute things that you could never ever imagine computing otherwise. Then there will be no doubt about that thing being useful. And so with that as the background, I want to start asking you, what do you want to learn in the lecture now? And if I gave you a large quantum computer, what will you do with it? I think it's the latter that we may want to start with having the conversation. What would you do if I gave you a quantum computer with, let's say, a few thousand qubits? What would you do with it? Well, so we can start with one topic with the solve physics problem. For example, many-body localization. Is that all we're interested in here? Catch up to that. Oh. What would you do? Why are you interested in quantum computing?
I think for me, physics problems as well. It's
physics problems?
Yeah, simulating.
One more. And for you?
I think I would be interested in all this cryptology, like all the information can go on, like the security. And
Security, cryptography.
Yeah.
Right, so you have things about cryptanalysis, code breaking.
Yeah.
That's an interesting topic to discuss as well, yes. Why are you interested in that? What really, or would you use it?
I mean, I think there's so much information goes around.
Yeah.
And we really don't know where all the information goes and how.
Yeah.
So maybe we can try to find a new way to store the information.
To make it more secure or to break it? What is your interest?
I want to answer this question in a second.
Good, okay. I'll share my thoughts around that later. Else? Physics problems. One more. Yeah.
Machine learning.
Machine learning. Good question. Yes, machine learning. It's another nice topic to discuss.
Design of new drugs, for example.
Drug design. We need to discuss.
simulate biological system.
Simulate biology. I just want to create a question. What else?
Optimize the production of fertilizers. Well, to make sure that it takes less energy resources to
So, yeah. Let's call that by the catalysts in fact. Because we can do more than just fertilizer. We can also do maybe to cleaner cars, capture carbon from the air. What else could we do?
Neuroscience, cognitive science.
Neuroscience. Yeah. What else? Yes, here on this side.
Protein folding.
Protein folding, yes, sir. Aber that mentioned often. Good point. What else?
Gravity, quantum gravity, maybe again.
Okay, does that for the physics problems?
Astrophysics, cosmology.
Gravity, cosmology, quantum gravity, cosmology. We're just brainstorming now. What else could we do?
Factor of really large numbers.
Factor of really large numbers. Can we have that as part of good analysis?
Oh,
Whoa.
recreational mathematics.
Yes. That's also there, yeah. Anything else from this side? We didn't have so much yet. Yeah. What do you all want to learn? What I would do with it, and what I would suggest, and that we go through that. So yes, the starting point is always we want to get a machine that can solve problems that they cannot solve classically. And because let's say classical computers are not there yet, but if they were 1,000 times bigger or faster, then they could do it. But I think it's much easier to invest the money to just build a bigger and faster classical computer. And we'll still need 5 or 10 years to build a large quantum computer, and then I will also have a faster classical one. So if we say it might take €1 billion, like in a flagship project, to go towards a quantum computer, you could ask, could you solve the same problems just investing €1 billion directly to solve the problem? You really want problems that are beyond what we can do classically. That's one thing, a really hard problem. And then the second thing is, these have to be problems where quantum computer can help. It just being a big problem doesn't mean quantum can help. It's not that magic wishing well that solves my problem. Sometimes when I ask that, people tell me, yeah, you can cure cancer with a quantum computer. Then I ask the question, okay, how do you want to do that? So I want to now go that step deeper and ask kind of, for these problems, how would we use a quantum computer to solve it? Then we will come here, and quantum computers are so fast that they can do much more than a classical computer. And I'll come to that, and I might use factoring as the example to show what are the pitfalls there. Because a quantum computer is not faster than a classical one. A quantum computer will actually be slower than a classical one, but it's more powerful. Each operation will take much longer, but quantum superposition can help us do things that are just hard classical. So let's look through that list. Solving physics problems. When these are quantum problems, then yes, the quantum computer can simulate a quantum system, and that's one thing we'll look at. So here we can solve quantum systems more efficiently than classically in many cases. That's a good application. But we need a model that is well defined. If somebody says quantum gravity, then if you have a quantum model to simulate there, then it's fine. If you say want to solve the problem of quantum gravity, then the quantum computer can help you towards that by letting you simulate some models. But you still have to know what you want to solve. It's not that wishing well. Cosmology is an interesting question. Or I often also hear things like climate prediction, weather prediction, and things like that. We have to think about what can quantum computing help there. And so for these physics problems, we need to think about what is it that makes the problem hard. Let me take as an example weather prediction. I want to have more accurate prediction for tomorrow's weather. What do I need to do that? I need to solve the Stokes equation for the airflows and radiation and cloud formation and so on. So I have a very complex system of coupled nonlinear partial differential equations that I need to solve. And once I've solved it, I need to know the weather everywhere. So I have as data the temperature, wind speed, the pressure, and so on at the locations. That's the starting point. And then I propagate it forward in time. And it's a nonlinear partial differential equation I solve. And then I read out where I get to. There are a couple of things to observe around that. The first is the complexity of solving the equations classically is proportional to the number of data points and to the time that I propagated with. It's linear in the time and linear in the number of grid points. So I have the weather, let's say on a mesh like this, to the number of mesh points times the time that I want to propagate. And one can prove that there's actually the lower bound to compute it ever. Because I have to do one time step after the other. There's no shortcut. So the time I need to compute has to be proportional to the time, and I have to propagate each point forward in time. So since the classical algorithm already has the optimal scaling, a quantum computer cannot really help me much. So we have to see what is the complexity classically and what is it quantumly. The other challenge is, so maybe there's a shortcut, but the Schrödinger equation is a linear partial differential equation. And if you want to solve a nonlinear one, then the question is how can special purpose hardware that implements a linear partial differential equation help me with something nonlinear? So nobody has found that yet, and one can actually prove that if one could exponentially accelerate the simulation of a nonlinear PDE, then that will solve you many problems that one believes cannot be solved ever. So there are ways to prove that we cannot exponentially accelerate something nonlinear. But so that's one of the basic principles I want to apply to the list here. Is that a problem that is just super hard to calculate? Or is it something where quantum mechanics can help? For solving a physics problem, if you want to store the wave function of a quantum many-body problem that needs exponential memory classically, it needs only a linear number of qubits. There's a big advantage there. For weather, likely not. Cosmology, there the question is, what do you want to solve? Is it the classical problem of how the cosmos expands, the gravity problem? Then likely it's hard to accelerate it. Are there some quantum problems in there that one wants to solve? Those will be interesting. So it goes down. So when we want to solve physics problems, let's solve quantum physics problems. That's a good application. Let me jump from that to protein folding or drug design. These are problems that also come up often and that are related. The question there once more is that a problem that is just hard classical physics? Or is it a problem of quantum physics? Where is the computational complexity? If you say you want to calculate the forces more accurately as it folds, that's a quantum physics problem. Do you want to solve the folding process more efficiently? The folding process is similar to weather. I have something that I evolve in time. Move it around, and again, I cannot accelerate that if I do it as a classical simulation. So if I view protein folding as a classical physics problem, where I have some kind of ball and stick model of the protein, and it folds around, and I have classical force fields, then, okay, there's a classical physics problem. The folding, I cannot simulate it faster than the time it takes to fold. A quantum computer cannot help. If you think the problem is that actually the classical model is not good enough and I want a quantum model for it, I want to really calculate the forces quantum mechanically, then the quantum computer can help. Because I can really get the accurate forces quantum mechanically. But the simulation will immediately become 1 billion times slower. So if the problem is already that the classical protein folding is too slow, the quantum computer will not accelerate it. If you think that you can fold it, but then the energies are not good enough, or the forces are not accurate enough, that's where quantum can help. So that's why I call this kind of, for the standard model of protein folding, quantum computers will not help. If you need better forces, they can help. Similarly in drug design. In drug design, you want to find a drug that just fits something, that fits a receptor. And so I want to find a molecule whose state kind of fits somewhere. If I can calculate the structure of the drug well enough classically, then I don't need a quantum computer. Then I just have to go through millions against millions of drugs and try to find out which one will match nicely. If the classical model I have that I can solve classically is not accurate enough, then again use the quantum computer to solve it more accurately. When we talk to pharma companies and ask them, what is your problem? Are your simulation codes too slow? Or are they not accurate enough? Then they say they are far, far too slow by big factors, and they go to even crude approximations. They're still too slow. So it's a question of speed of the classical simulation, not yet a question of accuracy. And so for drug design, we haven't yet found the problem where quantum computer can help. Just, yeah?
How about quantum annealing? Is this a hopeless cause? Is this like with always Monte Carlo?
Quantum annealing is an interesting thing. There's missing here. Yes, we've missed.
Quantum annealing optimization, which would like be quantum folding.
We're missing optimization. Yes. So now you can say you can do it as optimization. If don't fold it with dynamics, fold it with an optimizer. Can quantum optimization help with that? Good question. One doesn't know, but we did experiments and we know something about that now. That's something to look into. So let's look at that a bit later. Optimization. Let's look at the quantum physics problems. Can quantum annealing help? And say, yes, quantum annealing can help. Do we need quantum hardware to do quantum annealing? That's another interesting question. That's still open. So protein folding, drug design, it's more a classical problem. But the catalyst, that's a chemistry problem, and again it depends on, is this a chemistry problem that I can solve well enough with classical methods or not? When it is mostly organic molecules
with s orbitals and p orbitals, then the correlations are weak, then density functional theory is good enough, Hartree-Fock methods are good enough, mean field methods work well, then you don't need a quantum computer. The moment you include heavy metals with d orbitals and f orbitals, then it becomes harder. Then things are correlated, and then it goes back to solving an important quantum physics problem. So that's where a quantum computer can help. Machine learning, if we jump to that. So this is something that's also green, and we'll look a bit into that. Machine learning. Interesting open question. We can start with it now or later. If you want machine learning, the hope is, yeah, why do you think it helps for machine learning?
Well, machine learning is multiplying big matrices, and that's what quantum mechanics is about.
Machine learning, it's multiplying big matrices, but then these big matrices are based on data, right?
Yeah.
And now let's say I want to multiply a matrix of size n squared with a vector. Right? I want to take a vector, multiply it with a big matrix. Now we really have to see, if that's what you want to do, if you say you really want to do a big matrix vector multiplication, then if that matrix consists of data that you have to load from somewhere, the time you need to multiply it is the size of the matrix, so it's n squared. And you cannot make it faster because you have to load the data. If it's a quantum computer, a classical computer, it doesn't matter, you have to load the data. So again, we're back to like weather and climate simulations. I have to load the data somewhere, and that limits me.
Well, I guess the promise of quantum machine learning is that machine learning is about finding correlations in your data.
Yes.
And the quantum computer can give you correlations which are impossible to produce on a classical computer.
Yes. Okay. Yes. So let's start with that maybe, because that's a good point. So what basically machine learning is, you want to. So who here is familiar with machine learning? So machine learning, it's basically very simple. You want to find a function approximation to something. So I have some data, and I want to find a function that models the data. That function could be that if the input is a picture of a cat, the output is cat, and if the input is a picture of a dog, the output is dog. So it can be super complex functions like that, or that it helps you drive your car somewhere. But basically, deep down, it's always you want to approximate a function. So you want to learn a function f of some data x. And that should give you something. And then you have some parameters, let me call them theta. And you want to choose the theta, and that's your function so that's your model. So you have a model of x and theta, and you want that to be as close as possible to some unknown function f of x. For example, that gives you, for cat pictures is a cat, for dog pictures is a dog. For car pictures it says car or whatever. And so you make some general ansatz, some model, and you have some fit parameters data in there that you want to choose so that this model approximates your function as well as it can. So what you have to do is you have to just find those data parameters. It's a fit, essentially. And so that can be viewed as a black box. Here where you feed in your data x, you get out your values y, and it should be close to the f of x, and you have some dials there that you adjust the value of theta 1, theta 2, and so on for your black box, and you choose them until the model is pretty close to the function that you wanted to learn. That's classical machine learning. In quantum machine learning, you just use a quantum black box, but it's again just a function. But now we know that a quantum computer can evaluate some function efficiently that no classical computer can ever evaluate. So the class of functions that I can implement with a quantum computer are bigger than the class of functions that a classical computer can efficiently evaluate. And so the most promising idea is, yes, I just use a quantum function in here. I use a quantum computer to do it instead of a classical one. And quantum computers can evaluate more complex functions, so there may be more correlations in there. And so there's big promise in that. Do we know whether it helps? Proof of principle, yes, we know. Because let's assume that function is actually, I'm observing some quantum state. I do a quantum experiment, and I want to get out the result of that quantum experiment. So there's some quantum process that happens. If that quantum process is a quantum many-body system, then we don't believe there's any classical method that can actually accurately describe it. But if I put in a quantum model, a quantum function, that quantum computer could do it. So what we can show is if you have the output of some quantum program, some quantum circuit, that I cannot simulate classically, I can still simulate it quantumly. And so I know there is a quantum function that can represent the data. But classical functions might need an exponentially bigger machine. So from that we know that in principle such a quantum model can describe quantum data that is hard to describe classically, and there's an exponential advantage. But what about classical data? What if I don't care about quantum data? What if I just care about weather prediction or driving my car or whatever, or the stock market? If I care about classical data, is a quantum model, a quantum function, better at learning classical data with strange correlations than a classical model is? Do you know the answer?
Does anyone?
No. We don't, but there's a big promise. If you can find that actually there's some data that a quantum model can learn much better than a classical one, there might be a huge application, extremely broad. But we don't know if there is one. So many people have tried. And what often happened, and that will be similar to optimization then, what often happened is people compared and found, yes, quantum models can learn classical data, great, that's the first step. But they didn't learn it better than a classical model. They were just as good as the classical model. Then sometimes people find that, hey, now it seems that it's better, then somebody else finds a classical model that's even better. Or you write down a quantum model that learns something and you think that you're finally there to show, then you realize, oops, that quantum model can be dequantized. That means it gives you ideas for a new classical model, for a new classical function that learns it just as well. If that happens, I call this progress, because it gave me new ideas for classical machine learning. That's actually even better. Why is it better? Because I don't need to wait for the quantum computer. If thinking about the quantum model gives me a new idea for new methods in classical machine learning, then I can do it right now at scale without having to wait for the quantum computer. So it's impactful right now, but it didn't tell me yet whether the quantum model will be good. So here the big question is we just have to explore, and we have to try, we have to look for data that's hard to learn, and we have to play with various quantum models to find one that's better than a classical model. It might take us a decade to do that. It took people 30 years to find really how machine learning works with deep networks. So let's not give up after 2 or 3 years of quantum machine learning. But there's a big opportunity here to find a quantum model that can learn things better than a classical one. We haven't found it yet, meaning there's a big chance for any of you to find that, get a Nobel Prize or more, or become rich and famous. So that's an open question. I don't yet know. But that's the question there. Let's just quickly go through the rest here. Simulating biology, the question again is like in protein folding, do you want to simulate a classical process or a quantum process? If it's a quantum process, yes, it's again in the same class as the quantum physics problems. Do you want to simulate a classical process? It's unlikely that a quantum computer can help. Do you want to optimize something? We'll come to that. So if there are not more proposals for what you could do, then I would focus on 3 topics here. One is kind of simulating the physics or chemistry, that's roughly the same. Optimization would be one. And if there's interest, kind of the factoring problem, we could also look at that. Are there more topics that you want to go into? Or do you disagree with something I said here and really want to discuss about quantum for climate modeling? I think we do that with some wine or beer afterwards. So let me maybe start with showing why. So I might like to start with the cryptanalysis one, since that came up here, because that's a beautiful example that shows how quantum computers are exponentially more powerful than classical ones, but also extremely limited. And that may give you some ideas for how to think about the power of quantum computing. And yeah, I could just jump to the next slide. Yeah, because naively, one can view that quantum computers enormously accelerate some calculations by operating on all inputs simultaneously. I take my quantum register, like a classical one, and classically, it can only store one number. It can be 0 or 1 or 2 or 3 or 4 or 5 or 6 and so on if I store an integer. Quantum mechanically, it can be in a superposition of all possible inputs. As we know that, and so one can naively say the power of quantum computing comes by the quantum computer being able to calculate on an exponential number of inputs at once, and so it's exponentially faster. That's one of the myths that needs to be debunked here. It does it, but there's a limitation, and that's what I want to show. But before that, maybe let's just think about how powerful that really is. Because if I want to store the wave function of 1 qubit, I need 2 numbers, 2 complex numbers, 16 bytes. If you want to store the wave function of 10 qubits, that is 2 to the 10 values, so I have 2 to the 10 or 1024 complex amplitudes, so I need 16 kilobytes to store it. I can simulate an operation on my watch in a few microseconds. For 20 qubits, I need 60 megabytes. I might have to pull out my smartphone. For 30 qubits, I need 16 gigabytes. It might take now a second or so on my laptop to do an operation. For 40 qubits, I need 16 terabytes. I go to a big cluster. 50 qubits, I need 16 petabytes. I go to the biggest supercomputer that will be built this year. And then every 10 qubits more, it's a factor 1,000 more in memory. So with 60 qubits, I need 16 exabytes of memory. That's maybe the computer will build in 10 years. 70 qubits will need 16 zettabytes. Maybe we'll do that in 20 years, but as I make the computer bigger by a factor 1,000, also the power consumption goes up. And we just may not be able to afford the power for that. But if we go to 270 or so qubits, then I need more memory than there are atoms in the visible universe. So there's soon a limit where I just cannot do all those things in parallel. But there are also limitations. So let me show that maybe, or discuss that using the examples of factoring, which is a great example here. And let me just find the right place and show you kind of what are the advantages and where is the problem with quantum computing.
Do you mind to move to that?
Sure. So why is it so hard to find a quantum algorithm? So this is the general structure of any quantum program when I want to compute something. So any quantum math or so. I start with the quantum register in just a single state. Let's call it 0. So it's a classical state. I'm just in the state 0. And then I prepare my inputs. So I prepare all my inputs in a quantum superposition of all possible values. So I can prepare, for example, a register with all possible input values. And then I compute. And that's correct. And now compute in superposition on exponentially many values. And I get some answer. But let's say I get there. And let's say I measure. What happens when I measure? The wave function collapses to one value, right? So I might start from a wave function that is x and the result y is 0. Then I'm computing that and it gives me x and f of x. A super complicated function, and I'm in a superposition of all possible x. But if I measure, it collapses to a random x, and I get the function evaluated for that random input x. I only get the value out for a single input when I measure. So it's the output problem. I could just as well have chosen a random value x to start with, do the computation classically, and get the same information. So yes, I have all these exponentially many values there, but I cannot access them with less than exponential effort. So the trick then is you have to do some reduction operation. You have to somehow do something with the superposition to learn something of it, to collapse it to fewer values, so when they then read out something random, that is meaningful. So that's one challenge. The other challenge that makes it hard to implement it is this is a pure single instruction multiple data or SIMD computer. So on all the values, I'm evaluating exactly the same function. Doing branches like if statements is hard because I do the same operation on all. And quantum mechanics is reversible. I can always undo it, so I have to implement it in reversible logic. That also makes it harder. And I do it on a quantum computer, which is slower than a classical one. So it's more complex. But the power of being exponentially better is intriguing. And so the main challenge is getting this reduction right. And let me just show that as one example of factoring. Factoring a small number like 15 is easy, 3 times 5. If I tell you 21, you tell me it's 3 times 7, right? If I give you this number, can you tell me the prime factors? Someone suggests you want to use a quantum computer to factor really large numbers. No, I can give you the answer. Here it is. It's easy. How did I do that?
You went the opposite way.
I went the opposite way, right? I took 2 prime numbers and multiplied them. This way is easy, that way is hard. And that forms the basis of the Internet's public key cryptography. Multiplying 2 prime numbers is easy. Finding the prime numbers is hard. If I give you the product, I can encrypt data. So I can share the product with you. You can use that to encrypt data, send it to me. And only somebody who knows the prime factors can decrypt it. They're super useful, and that's the basis of public key cryptography. Now, on a quantum computer, Peter Shor found that's easy to do. This is polynomial complexity in the number of digits on a quantum computer. So if we have a quantum computer, we break this. There are now two discussions to be had. The first is, what do we do about it? And the second is, how does a quantum computer do it? So for the first one, what do we do about it? Do we say, yes, we've won, we have found a commercial application of a quantum computer? We would say maybe not, because this is not commercially valuable for any company. Because if you build such a machine, people will stop using public key cryptography and the use case goes away. So what we'll do is, and people have started working on that already, we need to find new cryptography methods that are quantum resistant, for which we don't know any way that a classical or quantum computer can crack them. They are called post-quantum cryptography schemes. They exist now. They are being tested and they can already be deployed and used. So it means that once we have a quantum computer, we will switch to post-quantum crypto schemes and e-banking will still be safe. The only people who have problems are those who send secrets around today, encrypted. Somebody intercepts those and decrypts it in 10 years when they have their quantum hardware. So if you have a secret that you don't want somebody else to know in 10 or 20 years, then you have to be careful now. The best is don't send it by email. So, but what Microsoft does here is that we work on the post-quantum crypto methods so that in time we can deploy them and you stay safe. But how does the factoring algorithm work? Here's something that doesn't work. A naive factoring algorithm could be, well, I can work on exponentially many values at once, so let me just try to divide by any possible factor and find out what the remainder is. And I can do this, so I can prepare my register X in a superposition of all possible factors, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And then I can run a quantum algorithm to compute 21 modulo X. So I get the remainder after division by X. And that gives me 0, 1, 0, 1, 1, 3, 0, 5, and so on. So I get all of the remainders in superposition. I have divided by exponentially many factors at once. And I have this wave function. But now I want to find where the result is 0. So I want to find 3 and 7. And we have a quantum algorithm for that. It is Grover's search. It only gives me quadratic speedup. I can do that. I still need square root of 21 attempts to get it. It is still slower. So that will still be slower than the best known classical factoring algorithm. So we cannot really find where it's 0. What I can do is I can measure the result. And I might measure 1. And then I find 21 modulo 4 is 1. Yeah. And I try it again and again and again. And I have to try until I find the factor. And this is just random searching. This is not better than a classical approach. Because the problem is, when I measure the output naively, I could just have well started with the same random factor. There's no speed up. But I have to be smart to use the superposition. And that is what makes it hard to design a quantum algorithm. So we need that smart idea, and it was Peter Shor who had that idea. And it's not that you try factoring, but that you map it to a different problem where physics can help. And once I've shown you how it works, then you see it's totally obvious that this is where quantum physics can help and why it's a good problem. And he mapped it to period finding. There you can already see kind of the quantum connection. Period finding is like measuring frequencies, and that's something that physics can do well. So what is known from the Chinese remainder theorem is that if you know the period of the function, a to the x modulo n, if you know the period of that function and that period is even, then the greatest common divisor of a to the power of half the period plus or minus 1 and n is a factor of n. GCDs are easy to compute. The problem here is it's classically hard to find the period, because the period means you just have to calculate f of 0, f of 1, f of 2, f of 3 until it repeats. And that can be exponentially long in the number of your digits. But the quantum computer can do it better. And let's see how. Let's start with x being 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And let's choose a, for example, 2. And I'm calculating now 2 to the x modulo n on the quantum computer in a superposition of all possible values. I get 1, 2, 4, 8, 16, then 32 modulo 21 is 11. 11 times 2 is 22, modulo 21 is 1, and it repeats 1, 2, 4, and so on. So classically, you have to go through that 1, 2, 4, 8, 16, 11, 1, and then I see the period is 6. I see the period is 6, 6 is even, and then now this is 2 to the power of 3, which is 8 plus minus 1. 8 minus 1 is 7, that's a factor. 8 plus 1 is 9, and the GCD of 9 and 21 is 3. That's the other factor. So it works out. But how do I find the period without going through it? On a quantum computer, I could just measure the output. If I measure the output, it collapses. Have we gained anything? No. Right? 2 to the 4 is 16. Yeah, I know that. It doesn't tell me anything about the period. So let's not do that. Let's start over again. And the trick by Shor is he measures just the function value. You don't measure x and the function, you just measure the function value. What do you get? You get a random function value like 2. But the magic here has happened with entanglement. This is 2 here, and the function is, and the wave function is now in a superposition of all the arguments x whose function value is 2. So the function register has collapsed to 2. The x register has collapsed to all those values x whose function value is 2, 1, 7, 13, 19, and so on. And they're all spaced apart by 6. I can't measure them because then it might just get 7 and haven't learned anything. But now the trick is to perform a Fourier transformation. This is spaced, for example, 1, 7, 13, or it might be 2, 8, 14, or it might be 3, 9, 15. It's spaced apart by 6 with a random offset. If I do a Fourier transform, I don't care about the random offset that goes into a phase, and I just get multiples of the frequencies. So I get 6, 12, 18, 24. If I measure, what do I get? I get some random multiple of 6. I can try the second and third time, and I get multiples of 6, and I can very easily find out the GCD so that it's 6. So doing the Fourier transform is the trick here. That's the reduction. With the Fourier transform, I can actually measure and read out the period and solve it. So that's the general trick that we need. It's not so easy that I can calculate on all values at once. I can. But to make it useful, I need that trick afterwards, the reduction, to just pull out something. The period, like the frequency, that's something easy to pull out with physics and do a Fourier transform. In general, it's hard, and that's why it's so hard to find new quantum algorithms for math problems. But so that's the basis here of the Schwarz algorithm. I measure the function value, and then I can just get the period. And with that, yes.
But how do you know that that number could be a prime number? Because you get a r over 2 plus minus 1, but you still need to find the prime number, right? So you want to decompose prime numbers.
No. So I want to get a factor. So here what I could get out is I could get out period is 1. Then I just try again with a different value a. Or I could get an odd number out, then I try a different value a. In this case, I get an even number. And when it's an even number, then in this case I know that that 2 to the 3 plus minus 1, so 7 and 9, both have the same factors as n. And so now I just need to find the greatest common divisor of that number in n, for example, of 9 and 21. And there's a simple rule to find out that that's 3. Or when it's 7, then no, 7 is a prime number, and 21 can be divided by 7, and I have both factors. But it might be that it's not even, in which case I change a and try again. It might be the period is 1, then I change a and try again. So that's the trick here. So that way we've seen kind of how quantum algorithms can solve problems that are exponentially hard classically, but how when you want to compute, it's hard to leverage the power of the quantum computer. Factoring is a key example here where it works. We would love to have more such examples. When we go to quantum physics problems, then it's easier, because in a quantum physics problem, yes, I have the wave function. It's described by exponentially many numbers. But when I do an experiment on a quantum system, I can never read out the wave function anyway. I can just do measurements. And so in a quantum physics problem, it's easier because all I can do is measurements anyway. And then I don't really care too much about it. I just want to make sure I can predict the measurements that I do. That makes solving the quantum physics problem easier. So are there still questions about cryptanalysis, or how we could use it, or how we can protect against it?
Well, I've heard, like, I don't know much about this, but I've heard said that people think that Shor's algorithm might be a very much a singular point, and that it's the only useful thing we might ever find in terms of
quantum computing.
In terms of something like this, not the physics problem.
No, so I think it can be generalized more to any period finding problem, to any hidden subgroup finding problem. It has been generalized to that. So we're finding structures, finding periodic structures. That's easy because that's what the Fourier transform can do, right? So, but now you can do it on complex computations. That is one of the few known cases with exponential speed up. There are other cases of mathematics problems with exponential speed up if you can map them to quantum physics problems. For example, if you can solve well-conditioned linear systems of equations exponentially faster than a classical computer can do. If you can efficiently propagate with a matrix. And I can quickly sketch how that's done. what you do there is I want to solve a problem like AX equal B. Then I prepare my state in a state, then I prepare my wave function in a state B. And then I want to apply to that essentially the time evolution with a matrix A, and I assume now the matrix is Hermitian. In case it's not, I have to just double the size and I can make it Hermitian. And if I can do that efficiently, then I can get the eigenvalues, and that's something I'll show you later. How can I find the eigenvalues of an operator? And if I can measure an eigenvalue of that, then with that time evolution, I can compute the eigenvalue. So I can take that over, I can add some other ancilla A, and I can take that over into basically B and have a... No. So I may have to explain that in a bit more detail. Let's see. Okay, so that will need a bit more background that I'll do after the break. But basically, what you can do is I can then take that over into the inverse of A times B. And the way I do that is, let me write B as a sum of the eigenvectors of A. So if the matrix A has an eigenbasis where A applied to a vector ui equal lambda I times ui, and if I can represent the vector B then as sum over I, some coefficient ci times ui, then I can write that here as, so then B is this, then if I evolve it with that, then I get the exponential of minus I at applied to B is now the sum over I of ci times exponential of minus I lambda it times the vector ui, because each component gets propagated with the phase here, with a different one. And now there is the algorithm that I'll show later that lets you measure that phase lambda. And if you now don't measure the phase lambda, but I can do it and put it into another register without reading out the measurement, but I keep it, so I want to measure it, but I don't measure it, but I keep it in like a superposition, then I can basically do that, and I have the eigenvalue lambda I here as well. So I have the eigenvalue lambda I of the eigenvector ui. Once I have once I have this representation, then I can divide by lambda I, because I have it here. And now I make a rotation, but basically I divide by lambda I. One over lambda I in here. But that means basically I've changed to the eigenbasis and I've multiplied with the inverse matrix. And then I evolve back in time. And once I've then evolved back in time, so if now after I multiply again, evolve with e to the plus IAT, then the phases all go away. And what I end up with at the end is then at the end B becomes sum of all the eigencomponent I, 1 over lambda I, the coefficient Ci times Ui, and that is just the inverse of A times B, which is the answer X that I want to get. So if I can time evolve with the matrix A, then I can solve a system of equations. There are two important assumptions here that I want to mention, and one that I'll ignore. The one that I'll ignore is that it has to be well conditioned, meaning the smallest eigenvalue should not be tiny, tiny, tiny small, but it should be pretty big. Or I really need to measure that with many, many digits of precision. The two important one is afterwards I get the solution X in a wave function. So I can only sample from it. I can't read out all components. I can just randomly draw some values from it. The other assumption that goes into it is I have to be able to time evolve efficiently with A. And if the matrix is a matrix of numbers that's stored on disk somewhere, there are n-squared numbers that I need to load into memory, the time is at least n-squared, and there's no speed up compared to a classical computation. Because classically can solve it in time n-squared. The time to solve a linear system of equations is proportional to the number of entries in the matrix that are non-zero. So if I have to load the real data, I haven't gained anything. But if this is a structured matrix, so that I can compute this efficiently without having to load data. For example, if it's a regular mesh and have just the Laplace operator on the regular mesh, and it's a structured banded matrix, then I can do that efficiently, and I can get an exponential speed up.
Except Laplacian structured mesh is not well conditioned.
The Laplacian on a structured mesh of finite width in high dimensions is well conditioned.
Really? But
when
the eigenvalue is roughly the size of the system with the infrared cutoff? And
yes.
The eigenvalue is 1 over the
What I'm saying now, yes, that's exactly it. What I'm saying now is if you take, if you keep a fixed lattice spacing, okay, and you do not make the lattice spacing finer, but you increase the number of dimensions. That's how you can get something well conditioned. I just don't know why anybody cares about that problem yet. We can show that can be done efficiently. It takes about 10 to the 10 gate operation, will run for a few hours. I haven't found the application of that yet. Most linear systems are not well conditioned. Then you use preconditioned and more to make it well conditioned. And there has been a paper that tried to take a scattering problem and use this exponentially speed up algorithm that has exponential speed up over the best known classical algorithms, and they calculated what it would take to solve a problem that they can do in a few hours on a supercomputer. And the answer was it would take about 10 to the 28 qubits, and the runtime it's about 10 to the 29 gate operation is the depth. If you can maybe do a 1,000,000 gate operation per second, then it would be about 10 to the 23 seconds, which is about 10 to the 16 years, or orders of magnitude larger than the age of the universe. The algorithm has exponential speed up. That's one point I'll make then is, or that I make now before the break. We need not just the exponential speed up, we need more. So let me quickly jump to a slide where I have that summarized for you. So to get a quantum application that has speed up, there are 3 things that I need, or 4. First is I need to find a quantum algorithm with exponential speed up. And we found one here for well-conditioned linear systems. For example, then next, you have to check that the quantum speed up is still there after you implement all of the I/O. That is, in this case here, if the matrix A is given by numbers stored on disk somewhere, and I have to load the numbers from memory, have to load n squared numbers, it cannot run faster than n squared. So applying this will take time n squared. And in time n squared, I can solve the problem classically. The quantum algorithm can solve it in time log n, but that means I'm not allowed to load numbers here. And there's also a big problem with machine learning. If you want to use a quantum algorithm for machine learning training, then I have to load all of the data from disk. And if it is petabyte of data, then it cannot be faster. So quantum algorithms help when it's structured data, when I'm computing something. And then the next thing to check is what is the runtime. Have to optimize the code until the runtime is short enough. I don't want to wait 10 years. I don't want to wait 1,000,000 years for that, but it has to be short enough. And after that is done, then I want to wait for my quantum computer and run it on there. So I'll show you something of that then after the break, and show you kind of how that problem can be solved for the simulations of quantum systems. Or I could tell you something on quantum annealing. What would you prefer? Quantum simulation or quantum annealing, or should we keep both a bit short and do both? Both? Okay. Okay, then let's do both afterwards, but not in deep detail. Okay, good. But we still have 2 minutes before the break officially starts, so are there any questions?
So you said earlier that if you could fast forward nonlinear PDEs, then this would solve any problems.
Yeah.
But I mean, you can already show that it's impossible to fast forward, for example, Hamiltonian evolution.
Yeah.
So, I mean, you would solve all the problems
if it's fast forward to, if it's impossible to fast forward a linear,
yeah.
And it's impossible to fast forward
nonlinear as well. Okay.
A nonlinear as well. Yes.
So that's this kind of thing.
Yeah. And if you have to read in the data, then you know you've lost, because the classical algorithms are linear in the data size or in the mesh size, and the quantum algorithm can't be faster. Yeah.
Well, at the beginning, you asked us what our ideas were with
yes.
the quantum computer. What would you do with the quantum computer then?
I became interested because there were certain quantum physics problems, frustrated magnets, Hubbard model, and so on, that I couldn't solve. In quantum Monte Carlo, there's the so-called sign problem that bothered me for many, many years. My master's thesis had problems because we encountered the sign problem. That's when it first came up. And so if I now have a machine that can solve the sign problem of quantum Monte Carlo, then I'm excited and I want to use it. And so I've worked on simulating quantum physics problems for many decades. And initially, I was frustrated by limitations we have. We cannot do real-time dynamics for big systems, or there's the sign problem in quantum Monte Carlo. But then over time, I saw myself thinking, yeah, I can do that if I just had a quantum computer. And that was the point in time where I said, yes, now I need one, and so I'll help build one. So my interest for me academically is solving the quantum physics problems. The impactful application is going beyond the simple quantum problems to chemistry problems, to material science problems that can really solve problems of interest. The second thing that I found also, having a good fast optimizer, having a quantum annealer that's better than a classical annealer would be really amazing. And this is how, as I'll show you after the break, that is where we succeeded. Because we found out by studying quantum annealers that they are sometimes amazingly fast and better than any known classical algorithm, but I can simulate it efficiently on a classical computer. And that means I can actually run quantum annealing efficiently on classical hardware now. And we can solve problems that were just not tractable so far, classically. Of course, it's kind of cheating because I do it on a classical computer, but I wouldn't call it cheating. I would just say that by thinking about the quantum algorithms, we found better classical algorithm, and that's a win. And once we have a quantum computer, we can run it a bit faster, but I think the main advantage we have already there. So it's the quantum physics problems and the chemistry problems that I'm most excited about. So that's what I'll show you after the break. Okay, so we have 1 hour. Let me spend half an hour on quantum annealing and half an hour on quantum simulation. So for quantum annealing, the basic idea was that if you want to find a global optimum and you're stuck in a local one, then it may be better to quantum tunnel through the barrier to find the global one than to climb over the top of it. And the first time that was done was by the group of the athlete, now 21 years ago. They looked at the spin glass magnet and found if they cool it down just as a function of the temperature, that's worse than if they apply a field transverse to the spins, heat it up, cool it down in a field, let the spins fluctuate around in the transverse field, and then only cool down. And so in this process, I may need to show one more slide here that's not in the deck. Let me get another one. So the basic idea in quantum annealing is you have some problem like a spin glass problem, but now I don't solve it directly by cooling it, the IC model, but I apply a strong transverse field to it, that I first have all the spins aligned in the field direction, and then I adiabatically ramp down the field strength. I ramp up my couplings, and I adiabatically go from that state with all spins aligned with the field to the ground state of the spin glass problem. So that's the basic idea here, and that's what the quantum annealer implements. So that was done here. They applied the transverse field, a strong one, cooled down in the field, and then switched off the transverse field, and they found a state that looked better. There was also a paper in Science where people simulated that and found that as a function of an annealing time, the quantum annealer reaches lower energies than the classical annealer. So that just the thermal cooling was less efficient than the quantum annealing, where I don't just cool in temperature, but where I start with a strong transverse field and slowly turn that off. So where the quantum effects seem to get me the better state than just the thermal cooling. And then we tried to look for that on the quantum annealers by D-wave and looked for a certain class of problems at the simulated annealer, a classical one, and the quantum annealer of D-wave. And we looked at easy problems and hard problems. So let's just look at the green curves here, which are the median hardness. And we found that the scaling basically for the median hardness was the same. The scaling for the hard problem was the same. So we always found the same scaling of the time to solution here as a function of the problem size. If quantum annealing had been really faster, then I would have expected the quantum annealing curves here to asymptotically be flatter than the classical ones. But we didn't see that. And that was a question then. Why did all the theory and simulations predict that quantum annealing should be better, and we didn't see it in experiments. And so then we started looking at that. And so let me show you how do I do classical annealing. Classical annealing is basically I take a system and I cool it down slowly. So let's say I want to find the ground state of my Ising spin glass model. I take my spins, have my couplings, and I simulate it in a Monte Carlo simulation based on the partition function. I simulate it, I flip my spins, I cool it down, and I find the state. If I do it slow enough, then I might find the ground state. If I want to do the same thing for a quantum system, then I take my quantum spins, I put them in this big transverse field, and I simulate it as I slowly reduce the transverse field. And I reduce the quantum fluctuations by reducing the transverse field until I find the ground state. But how do I simulate that? It's just hard to simulate real-time dynamics of a quantum system, right? So we need a quantum computer. Let's come to that later. But if I say, okay, I get slowly enough, and in this thermal, so I can always simulate the thermal properties of the quantum annealer at that time, and then I slowly change the field strength, I slowly anneal, and always simulate the instantaneous thermal properties. That's what we can do in the quantum Monte Carlo simulation, because I simulated quantum annealing. In this case, I have to simulate a quantum system. And the partition function of the quantum system is the trace of exponential of here minus beta h. And that is hard to calculate. That is not like a classical partition function. But what one then does to simulate a quantum system, we actually map it first to a classical system. So we do a path integral representation where we represent the exponential of minus beta h as many small time steps in time, in imaginary time, and we do a path integral. And we always propagate by small time step delta t. Then again, I get to my next quantum state. So I do lots of small time steps, and I map the 2D quantum system, in this case, to a path integral where I propagate that state in imaginary time. Then I sample over all possible intermediate states. So this is the standard path integral with which I can map it. And if I take such a quantum spin model, in this case in a transverse field, then I map it, in this case, to a classical spin model in a higher dimension. So I can simulate any quantum system by simulating the path integral in one higher dimension. I can do that also for this quantum annealer. So I have my quantum spin glass here in a transverse field, and I simulate it by simulating the path integral lots of time slices, and now I just flip my spins randomly in a Monte Carlo simulation. This is what I do to simulate the quantum system here. And now we can explore, does quantum annealing have an advantage over classical annealing? And why did the D-wave quantum annealer not have an advantage over my classical system? And here's one thing that one of my students did as her bachelor thesis. She looked at what is the difference between what we did and where we found the D-wave quantum annealer did not have advantages over a classical annealer, and what was done previously when people showed quantum annealing has an advantage. And this plot shows the key results. What do I show here? Here I show, as I take a hard-to-solve spin glass problem and I simulate it with a quantum annealer, what is the energy above the ground state that I reach as a function of the time that I anneal? and is a function of the number of time steps I have in my path integral. So I have the path integral, and I split the interval from 0 to beta into m times steps. The physical limit is the limit when the time steps go to 0, so when the number of time steps m goes to infinity. What we find is, as we start with few time steps, it's pretty bad. As we go to more time steps, it gets better and better and better and better. And as I take the limit of m going to infinity, it gets worse again. So the physical limit of my quantum annealer simulated on the classical computer here with path integral Monte Carlo is that it's pretty good at reaching low energy states when anneal quickly, and then it gets stuck somewhere and it saturates. So there's a big dependence on the time step here. So for the short time step, the physical limit, I go down quickly and then I'm stuck. But the optimal time step, with which I reach the lowest possible temperature, is not the physical one. It's here I should choose about 20 or 30 time steps for beta 20. So if I choose a time step of order 1, then I seem to get to lower to lower energies than the physical quantum annealer can get. The physical quantum annealer here is the limit of m going to infinity. When I choose a bigger time step, then it's better.
But how is it possible? Shouldn't the physical annealer get to the ground state?
Yes, after exponential time, it will get to the ground state.
Okay.
It will. It just takes, yeah. If you run slower and slower and slower, it will reach the ground state. But if you want to reach the ground state, an unphysical annealer might be better. Can explain later why. So I can now look at that in two different ways. One is I want to really view it as a classical optimizer. If you want to view it as a classical optimizer, then I can just always choose the optimal combination of temperature and time step, so that I get the lowest possible energy. And then the quantum annealer is the line down here, and the classical annealer is up here. And the quantum annealer is better if I choose an unphysical time step. If I choose a physical time step, then the scaling of the classical annealer is better than that of the quantum annealer. The quantum annealer initially goes faster, but then seems to saturate, and the classical annealer goes down lower. So the difference is, how do you want to do the simulation? Do you want to do it in the realistic physical regime? If you do it in the realistic physical regime of tiny time steps, then the quantum annealer is worse than the classical annealer. To do the quantum annealer with unphysical big time steps, then it's better. How can it be better? Let's say I want to tunnel from here to here. This is the path I want to take. Or let me just do the following. How long do you think it will take me to tunnel through the wall here? A pretty long time, right? But now what if we make time discrete? And I ask you to close your eyes for a minute. And when you open your eyes the next time step, you will find me on the other side of the wall. Right? I can cheat. If you allow me to go to discrete time, then I can cheat. I don't have to go through the wall, but I can just jump through and you never observe me in the wall. Well, that shows you that actually quantum annealing is super useful if you start cheating. When you don't cheat, then for these spin glasses, it's worse than a classical annealer. If you allow me to cheat, if you allow me to view it as a classical algorithm, where I don't have to really be faithful to the physics, then it becomes interesting. And these old papers that showed that quantum annealing was better than classical annealing, At that time, they never had the idea that anybody would ever build a hardware quantum annealer. For them, quantum annealing was always the path integral Monte Carlo algorithm. And of course, they adjusted the time step so that it gave the best results. Because for them, it was just a classical algorithm run on a classical computer. The fallacy was then to take that and assume, because that is better, the quantum hardware should be even better. There was no proof for that, and it turned out that it was hard to find. So what we find here is quantum annealing can be performed in different ways. I can cheat with large time steps and use it as a quantum-inspired classical algorithm. That's super useful. Or I can work in continuous time. I can take the limit of the time step going to 0, and then I can really mimic the quantum hardware and assess its potential. In our case, it was worse. But now you may say, okay, that's nice. But the criticism is, what actually does the quantum Monte Carlo simulation of the path integral, what does that have to do with quantum annealing? After all, I said I cannot simulate the real-time evolution of the quantum system. That's too hard. So what I said I'm doing is, instead, I always simulate the instantaneous thermal state. And of course, with that, you can say, okay, of course, with that, you lose all of the quantum coherence. You don't get the effects. And it may be worse just because the quantum Monte Carlo simulation is not relevant for the physics of the quantum annealer. And so we looked at that. And we looked at that for a very simple test problem. But then based on that, we could also prove some theorems. And the test problem we did was just an Ising ferromagnet in a transverse field, in a weak transverse field. So the ground state then will be all spins up plus all spins down. And the first excited states will be all spin up minus all spins down. And let me now view that as an annealing problem, that I sweep a field maybe, and I'm stuck here in the left side, all spins up. And I want to tunnel over to the state of all spins down. I want to ask, how long does it take me to tunnel from all spins up to all spins down? And we can do that with the quantum hardware. They know the time it takes to adiabatically go from here to here is proportional to 1 over the squared of the gap. Right? That's what it takes to go adiabatically from one state to another, is 1 over gap squared. What does it take in the path integral Monte Carlo simulation? In that simulation, I start out with all spins up. And then at some point, I get 2 instantons. I get one kink where suddenly the spins flip to all down, and then they again flip back to all up. So if I plot here just the total magnetization, and then it starts at plus, it jumps to minus for a short time, and it jumps back. And what is the cost of that? I have to tunnel through it once and I have to tunnel back. And that is the matrix element to tunnel is the gap, and that's again the gap. So the probability for that to happen is the gap squared. The time until I get there is 1 over the gap squared. So what we conjectured from that, and what we also see here empirically in calculating, is the identical scaling. Here I show for 3 different strengths of the transverse field as a function of the size of my ferromagnet. In the open circles, the time I need in the path integral Monte Carlo simulation to tunnel through, and the filled dots is 1 over gap squared, so it is the time I need to go from one to the other with an adiabatic quantum annealer. And we find that actually it's identical. We find identical scaling. And we can then prove actually that the picture of the instantons, or the kink and the anti-kink, with that picture I can calculate the leading order term both for the real-time dynamics and the Monte Carlo dynamics. So I can prove that to leading order it's the identical scaling. So that's why that's relevant. But it gets nicer. Because why is the scaling 1 over gap squared? Because I have to go through, because when I do the path integral, that's the trace of exponential of minus beta h. So I have to go back to the original state. I start in a state, and after evolve to beta, I have to be back in the same state. So I have to tunnel through and I have to tunnel back. So I need to tunnel twice. And that gives me the 1 over gap squared scaling. What if I cheat even more than before? What if I just cut open my boundary conditions? I say I don't care about the trace anymore. I just make the boundaries open. If I make the boundary conditions open, then the transition state from one to the other just has a single kink. I pay only half the cost. And with that now, actually the empirical scaling, when you measure it, becomes 1 over gap. So the 1 over gap squared. So now I have two ways to cheat. One is I can make the time step bigger. But in addition, even more important is I can just make the boundary conditions open and simulate it. Now I tunnel quadratically faster. And so now we have an algorithm here that no longer mimics physics faithfully. I take a time step that is too large, I change the boundary conditions. I no longer faithfully mimic the quantum annealer. And so people building quantum annealing hardware say this is not relevant because it does not faithfully represent the quantum annealer what I simulate. My answer is I don't care. I have something that tunnels more than quadratically faster. I'm happy with that. And so what we found now is actually that dequantizing quantum algorithms can be super useful. So we can do the quantum-inspired solutions today. We take that. We actually map it to the path integral Monte Carlo method. We cheat in that. We make it quadratically faster. And that's what we use today. In the future, when we have a quantum algorithm, we can maybe make it even faster by implementing that algorithm with so-called quantum walks. But for now, what we've learned from studying quantum annealers is that not only can I simulate them, I can simulate them on a classical computer with a quadratic speedup. I don't need quantum hardware. I can do it for any model. So I can't just do it for Ising spin glasses. I can do it for any cost function I want, on any size system. I'm much more flexible and much more powerful, and I can do it today. Anybody can do it on the laptop even. So quantum annealing is useful, and then we applied it to a few problems in the energy utilities, finance, traffic, and healthcare, where we could use quantum annealing to solve problems that nobody else could solve before. One problem we looked at was magnetic resonance imaging. There we wanted to optimize the pulse sequence one uses in the MRI machine to get a better image. People just send in certain pulses typically to measure the coherence times of the nuclear spins and then get back certain times, and that the map to pictures. But our colleagues at the Case Western Reserve University found that if they send in a random pulse sequence and just map it to a dictionary and find, okay, that pi sequence gives that response, then that also works. You don't have to send in your specialized pi sequence to measure things, but you can just send in anything, even music, and you can decode it afterwards. Once you calibrate, and then they ask, could we use that to actually optimize the pi sequences to get the best possible image in the shortest time? And they wrote the grant proposal for that, and that was turned down because that problem is impossible to solve. Nobody can do it. So we use quantum annealing, and we managed to do it. This is the image we can get now. That was done, what was done prior. The experts will look at that. Okay, we don't see too much. The experts will look at, I didn't say that looks a bit better. When we then quantified it, we found that we can get the same quality image in 1/3 of the time. So you can do the scans 3 times faster. It doesn't take 30 minutes, it only takes 10 minutes. And that's huge. Or in the same time, you can get much more detail out. So those are real-world problems that we could solve with quantum annealing that nobody thought was solvable before. The market for machines to do imaging is several billion euros per year. If you make the machines 3 times more efficient, that gives some of the real value there. Second problem, we looked at traffic optimization. That was a problem that the company solved in 20 seconds on the machine by D-Wave. We had a student write the code with simulated quantum annealing. The first version of the code could do it in 200 milliseconds. The next version of the code done with 1 day more time brought it down to about 20 milliseconds. So problems that that company used to solve in about 15 minutes before, we can solve in 20 milliseconds with a quantum-inspired annealer on classical hardware. Why is it so much faster than on the hardware near quantum annealer? 2 reasons. First of all, we have speed up, as you saw. But secondly, the problem of finding traffic routing is not one that maps natively directly to an Ising spin glass. Each car has maybe 10 different routes to choose. And mapping that to an Ising model makes it much harder to solve. On the classical hardware, we can just use the native representation and solve it much better and faster. So there are lots of problems. So we can now do, for example, Seattle traffic. And if we had control over all cars, then we could tell the routes that make everyone be home 8% faster and 50% fewer traffic jams. So there's lots one can do very easily with quantum annealing, and it's useful already today because we can do it on classical hardware. So that's a success story, and we applied now also for energy and finance and so on. But you may be disappointed because ultimately it is just a classical algorithm running on classical hardware. It came from quantum annealing ideas, but ultimately it's a classical algorithm. You can call it a win because we solve real-world problems that make somebody real money. But I think for most of you here, that's disappointing, isn't it? If all quantum computing we're good for is making classical algorithms faster, then why do we even build quantum hardware?
What about this quantum walks that you mentioned? That you can improve on this further?
Yes, so with a quantum walk algorithm, you can take any Markov chain Monte Carlo algorithm and accelerate it quadratically.
And this is something like Grover search?
This is essentially the Grover idea applied on top of a classical algorithm. So I could apply that on top of the initial simulated quantum annealing. And then I get the same quadratic speedup. But the better is that I apply to the algorithm where I cheat. So I don't do quantum annealing directly because it's worse, but I take the simulated quantum annealing where I cheat. And I accelerate that basically with Grover's search to accelerate it quadratically. And then I get a quartic speedup over quantum annealing. So ultimately, quantum computer will help me. But it will be a while because quadratic speedups only win out very slowly over a classical computer. Exponential speedups are better. And fortunately, we have exponential speedups for solving quantum physics problems. So let's jump to doing real quantum physics problems. And I want to show you a few details of, let's maybe stay with something like quantum annealing. And let's just say we wanted to implement that. We want to implement some time evolution of a quantum system. Because that's a hard problem. So I want to evolve something in time, and I have a model. And let me assume it consists of a sum of many local terms, hk. And then to time evolve for a certain time, t, I split into small time steps. And it's super hard to evolve with an arbitrary model. But it can be easy to evolve under each of the terms separately, and I'll walk you through that. So what I can do is to evolve under h for a time t. I can make the time step delta t very short and use a Trotter formula to basically approximate that by evolving with each of the terms individually for a short time. So I approximate the exponential of minus I times the sum of the terms times t with the product of each of the terms. And if I make the time step small enough, then the error is small and can be ignored. And let's say I want to do that here for the Ising model in a transverse field, like we had in the quantum annealer. Then one term are the sigma c terms of the Ising model. And the other term is the transverse field sigma x with which I want to evolve. That one term here gives, so the sigma x term means I have to evolve, and that is I need to implement the exponential of I times gamma times delta t times sigma ix. So there's an I missing here. And the time evolution with the Ising coupling minus j times sigma c gives me an exponential of I times j times the time step times sigma ic sigma I plus 1c. So those are the terms that I need to do on my quantum state in the quantum computer. And the question is, how do I do that? So how do I implement the time evolution? And for that I use a certain number of quantum gates. So these are the fundamental operations that the quantum computer will have. And gates that I use is, one is the Hadamard gate. That's a gate that basically switches plus x state to plus c and minus x to minus c. So it takes 0 into the 0 or the upspins into 0 plus 1 and 1 into 0 minus 1. Then we have rotations around the x-axis, around the c-axis of a single spin. Exponential of your minus I theta over 2 times the Pauli matrix. And then I have the controlled NOT gate that takes xy into x and x or y. That means if x is 1, the second bit y is flipped. If x is 0, it is unchanged. So those are the fundamental gates with which I want to implement that quantum algorithm. That would be like if I tell you you have here a classical computer, and I give you an AND gate, an OR gate, a NOT gate, XOR gate, and so on. And you should build your code out of that. It's super hard to write a weather simulation based out of AND and OR gates. It can be done in principle, but that's the level. So what we actually then want to have is we want to build on top of that, the programming language that lets you also use integer numbers, and fixed point numbers, and floating point, and add numbers as but let's start with something very basic, close to the hardware. I want to simulate that quantum system. So how would I do that? How would I take my quantum state psi, and I want to propagate it in time? I want to propagate it, let's say, by the sigma x operator. So I want to propagate it, so I want to apply product over I, and I want to propagate exponential of minus I gamma sigma ix times step delta t applied to psi. How to apply a single of these terms? This is the exponential of something times a sigma x Pauli matrix. And if we look at the gates we have, there is the x rotation gate, where I rotate around the x-axis with an angle theta over 2. So basically applied to 1, this is just the rotation gate of an angle, and the angle is, okay, so I add a plus here, so the angle is minus, then there's a 1/2, so it's minus 2 times delta t times gamma. That's the x rotation Rx. By that angle around the qubit I. And you want to do that on every single qubit I, so I just write some for loop around. For I equal 1 to n. I do this loop. We apply the x rotation gate. That's easy, and so that's easy because basically the transverse field in the x direction is just the rotation around the x-axis. Then you could also add a field in the z direction that would just be rotation around c. Could add a field in the y direction, then you just add a rotation around the y-axis. So that's the easy part. The slightly harder one is the Ising term. Not to just show you, because once you understand how to do that term, then you can do basically all models. For the Ising term here, I want to calculate, here I have the exponential, well, that's what it is, e to the power of I, j, delta t, that's, let's say, sigma ix and the sigma jx. Sorry, sigma ic and sigma jc. How do I implement that on a quantum computer? Yeah, just need a 2-qubit rotation gate, right? And RCC. Well, okay, that would be cheating. How to do that with the gates that I have? I have single qubit rotation gates and I have a control NOT gate. How would you do it classically? Classically, you would just multiply sigma I and sigma j, right? We can do the same here. So what I propose to do here is in that, so to do that I can just do a C0 of I and j. What does that mean? It flips the spin j if the spin I is in the down state, if it's 1. Because, so in terms of bits, this is this x or the other one. So it's when this is, so this is at Diffständige modulo 2, if you view that as bit 0, 1. If you do it as spins that could be +1 or -1, then it's multiplication. So the C0 gate basically that means that means here this now becomes the product of the two spins. If you view it as +1 and -1. So with this now, the spin j contains the product of spin I and j. And then I can just do a C rotation by the angle theta here, or by -2 theta on j. And then now, of course, the spin j is now the product, but I need to get it back to what it should be. So I do that C0 again. And that uncomputes the product. So because when I flip it again, if x is 1, then I flip it again and now I flipped it back. So now I'm back in the original state. So this is the code to implement this rotation. And then I put that into a loop that goes over all possible terms. Maybe you're more familiar with quantum circuits. Who knows quantum circuits better than code? Have you seen quantum circuits before? Quantum circuits, yeah. It's basically just if you were to write classical codes and you write it with NAND gates like that. You don't typically write classical code like that because it's much more cumbersome. But one can do it deep down. And same quantumly. So this basically means I just do an X rotation gate. That's just a graphical form for that. And this one here would mean if I have the qubit I here and the qubit j here, then I do a controlled NOT gate, which is this symbol. I do the rotation here, and I do another controlled NOT gate. Circuits are what people might have seen before. It's just much harder to put such a circuit into a loop or into a code and to a subroutine. If I want to add the control flow around it, then it's much better to just write it as code. But for simple things, it's one-to-one the same. So that way you can now do products of spin terms. Let's say I want to do now, let's speculate and do something else. Let's say I have a model that contains the term sigma I x times sigma j c. How to implement that? How do I rotate under that? So we have the Hadamard gate. Remember the Hadamard gate that we have here? That basically flips the x, that switches x into c and c into x. So for this, I would do a Hadamard on I. And with that now, the x has turned into a c. So now I have to implement a sigma I c times sigma j c. Then I do a c0 of I and j. With that now j has become the product. So now it's just sigma j c. My new sigma j because that has become the product. Then I do the c rotation on j. And then I undo the rest to again separate it, and I flip the c back into x. So the typical form of quantum code is you do something here, you do a rotation, and then you undo what you've done. So that's the term u, that's v, and that's the u dagger. So you change the basis until it's trivial, then you do it, and then you undo the basis change. So this is how we implement, and there's nothing more to it. You just write your model as a term of Pauli operators. Then you change the basis until it's all c's. Then you multiply them with c0s. Then you do rotation, and then you undo everything. And that you can apply even to fermions and more models. So let me jump over to that and show you something there. What do you want to show for that? Yes, so how would I do it for fermions now? For fermions, I take the states, and they should now just represent the occupation numbers. For example, the upspin could be empty 0, and the downspin is 1, or the 0 qubit is the empty side, and the 1 qubit is the filled side. If you want to have a density operator, n, the density operator can just map to 1/2 times 1 minus the Pauli-C operator. A hopping term, like C dagger P CQ, becomes a sigma minus on P, a sigma plus on Q. But because it's fermions, I have to count how many fermions I jump over, because I have to make a Wigner transformation to transform the fermions to spins. And so the operator then has here a long product of sigma C terms in there. How do I implement that? Well, the sigma plus and sigma minus I can write as like a sigma mega x plus sigma y, or yes, other items here sigma x minus sigma y, and then the x and y convert to c's and so on, and then I do the same thing as here. And so this can be converted into code or a circuit that looks like this. So for each term that appears in the fermionic model, I can get some code piece or some circuit piece that I can apply. And then I can look, let's say, at the general Coulomb Hamiltonian. The general two-body Hamiltonian in a second quantized form that has the one-body term and the two-body term. Cp dagger Cq is the one-body term, Cp dagger Cq dagger Cr Cs is the two-body term. So it's just it's for let's say n sides, it's n to the 4 of these terms. For each of these terms, I write down a circuit to propagate it, and there are some nice quantum circuits or quantum codes for each of the terms that can do it. And and each one takes it most about kind of 4n gates. And I have n to the 4 such terms. So in total, I can propagate it with polynomial scaling, and it's pretty efficient. And with that, I can solve many models. And let me just show you. Yes, so with that, I can solve, for example, some quantum magnets, or a Hubbard model. It can be solved with about 1,000 qubits pretty easily. Let me show you what it takes to solve a real problem in chemistry. And here we looked at a simple problem with about 65 electrons and 57 orbitals, in this case for the nitrogen fixation catalyst. And we looked at what is the time it would take to do that. I have to, yeah, it's the right slide. So what's the time it needs to do that? And so what I do is I take the chemistry model for that, which is kind of the limit of what is just not doable anymore on a classical computer. And we find if we have a quantum computer with a logical cycle time for the fault-tolerant gates of 100 nanoseconds, that means now seems to be about a factor 100 optimistic. But let's assume we'll get to a really fast quantum computer that can do a fault-tolerant logical gate in 100 nanoseconds. Then that computation of something that is just beyond what I can do classically would take about 300,000 years. I don't want to wait that long until I write the paper. And that's why we sat down and we optimized the code. We reuse computations, we reorder terms, we wrote faster the codes for that, and we gained a factor 4 here, factor 4 there, some factors 10, some factors n, and then we brought it down the runtime to about 2 weeks. Now 2 weeks is something I'm willing to wait. Maybe, because then I just have the wave function once. When I measure something is gone, I have to start over again. So we still want to do it fast, and just in the last year we gained another factor 1,000 over that. So with that it becomes important, or useful. But what that shows is not just enough to say yes, in principle, using Feynman's ideas, we can write the code to do it. The code has to be fast enough. And thus, it is really important that we look further into how to make those algorithms even faster, to make it practical. Because just showing that it can be done in principle is great. It's the first step, as I showed before. Showing that quantum speed is the first step. Then you have to make the code fast enough. And so here we brought it down from 300,000 years to 14 days. We now brought it down about another factor 1,000. But actually, in the meantime, we believe that our quantum computer will be 1,000 times slower. So we're still at 2 weeks. We would love to do bigger systems, so I need your ideas to help me make something even faster. But with that, we can now really solve chemistry problems. And I wanted to end maybe with one last thing, because I promised to tell you how to get these eigenvalues that we discussed before when we looked at the linear systems. I want to mention here, so how can we actually get an eigenstate? So let me start here. All we talked about now was how to propagate a quantum state in time. What if I don't want to propagate a quantum state in time, but I want to find the ground state? What if I want to find an eigenstate? To find the ground state on a classical computer, I would just take some trial state and I would project it down to the ground state, either by multiplying often with the Hamiltonian or by propagating in imaginary time. And with that I can actually project out the ground state. On a quantum computer, I can't do either of these because a quantum computer is unitary. I only have unitary evolution and measurements. So I'm limited. I can work on a beautiful wave function. I don't need exponential memory to store the wave function, but I'm limited to unitary operations. So I cannot do what I can do on a classical computer. The classical computer, I pay the cost for the memory, but then I can easily project. With the quantum computer, I don't pay the cost for the memory, but I'm limited to quantum mechanics. I can only do unitary operations and measurements. So the way to get the ground state, or an eigenstate, is, you just measure. You prepare some state, some trial state, and then I measure the energy. And if I projectively measure the energy, then as we know from quantum mechanics, the wave function collapses to an eigenstate of the energy. So then I have the energy of the eigenstate and I have the eigenstate. And the probability of the state depends on the overlap of the eigenstate with the trial state. And so if I have a trial state that has a good overlap with the ground state, then with a good probability, I will always get the ground state. How do I measure the energy? Measuring the energy is not like I measure this qubit or that qubit, right? So how do I measure the energy? We do it by a process called quantum phase estimation, because as we discussed before, we can propagate a quantum state in time. We wrote down codes here for that, right? We can do that, and we can measure. So here's one easy way of doing that is let's assume I have an eigenstate phi n. And if I propagate that in time with h, then I just propagate it basically with the energy and I pick up a phase. And that phase is the energy times the time. So if I want to measure the energy, I have to measure the phase. How can we measure a phase? Who knows how we can measure phases? Interferometry, exactly. We can't measure directly, but we can do interferometry. So we have to propagate and not propagate. That's what I do is I take another qubit and I put that into the state 0 plus 1. And when it is 0, I don't touch the state. And when it is 1, I propagate. So I have two paths. When it's 0, there's nothing changed. When it's 1, I propagate. So when it's 0, nothing changed. When 1, it picks up the phase. And if I now measure the state of that qubit, then I measure the phase. So I do interferometry with one extra qubit. I measure that qubit. And by measuring that qubit precisely, I project to an eigenstate. The qubit measurement will tell me the energy, and the wave function will collapse to the corresponding eigenstate. That's quantum phase estimation. So basically simulate an interferometry experiment to get the energy in the phase. And if you look back here, and that's the same thing we do when we did the linear system here. For the linear, that was the machine learning. For the linear system, I said, okay, let me propagate in time. And when I propagate in time and I do it with an interferometer, then I get a qubit that contains the value of that eigenvalue. Where do you have it? Here, lambda. So that's how we can get the eigenvalue into the state of a qubit, which we then use to divide by that angle. And that way, that's how we solve the linear systems here. It's a bit more complicated, but that's the idea. So, and we don't have many more algorithms than that. We have the Fourier transform. We have the phase estimation algorithm. We have propagation of quantum states in time. And we have Grover search, which I didn't touch on now, because with quadratic speedup, it's hard to make it real in the short term. So those are the basic components that we have on quantum computers. We can use it for factoring. We can use it for simulating quantum systems. We can use it for simulating linear systems of equations. They work, again, just because it's a linear system. And quantum mechanics is linear. So quantum mechanics is really good at solving linear systems. For nonlinear system, it's harder. That's why the quantum annealer didn't have that speedup, because we don't know how to leverage it for something, for solving a nonlinear problem. It just gave us ideas for classical algorithms. But there are lots of problems in chemistry, material science that we can solve with a quantum computer that would be intractable on a classical one. And that's why I want to build a quantum computer and then use it to solve real problems. Thank you. Other questions?
So propagation in time, I mean, this is the thing which really we can do well.
That's the key, yes. Quantum hardware can propagate quantum states in time pretty well, right?
Yeah.
That's the basic premise.
Yeah, because I mean, finding the ground state, for this I must have a state which has a nice overlap, and this is hard to assume that I do. Okay.
I have ideas for that. Do you?
Pardon?
There are ideas for that.
I can do again optimization, I guess.
You can try optimization, yes. You can just try variation answers and just play with things and use an optimizer.
It's hardly universal.
It's hard, yeah. It's hard. You have to just make good guesses.
Yeah.
Or you can also use adiabatic state preparation. if you have some idea of what the ground state could be, then you can write down the mean field approximation of the model and of the ground state. And then you can prepare that mean field ground state because it's a product state. So then you prepare your wave function in that ground state of the mean field model. And then you propagate in time with the mean field model. And then you slowly interpolate from the mean field model to the full model. And if you do that adiabatically slowly, then when I adiabatically change the Hamiltonian during preparation, then I remain in the ground state of the instantaneous Hamiltonian.
What if the mean fields doesn't work, for example?
So then I get, okay, so then I get to something that is close to the ground state because I wasn't slow enough, I get too close. The phase transition is exactly why I want the mean field Hamiltonian. I want to break the symmetry, to not go through a phase transition. What if I guess the wrong symmetry breaking? Then I go through a phase transition and maybe hard. Yeah, that's why then I just try many different mean field models that could be the ground state. Or it could go from a non-interacting to an interacting, but that's hard because there might be phase transitions. If I can guess the right phase, the right symmetry breaking, then starting from the mean field model means there's no phase transition. And it's easy.
Okay, and for the, what are the interesting problems that I can solve using time evolution? Because just taking a state and evolving with time and measuring the result is hard, but not very,
Transport.
not very universal.
Transport properties. They're hard. Have a system, you turn on a power source, you want to know what happens. Or you use it for phase estimation to get eigenstates and get ground states. If you're interested in quantum Monte Carlo, you can solve the sign problem of quantum Monte Carlo by working in an energy eigenbasis. So just being able to project onto eigenstates is one thing you can do. What do you care about in a quantum system?
Phase transitions.
Then you want to just scan the ground state as a function of coupling strength.
Yeah.
Yeah.
Then, I mean, I don't know, say if I want to take a Hubbard and find if it has a superconducting phase transition.
Yeah, then you need to prepare the ground state. So you have to make guesses for what could be the phases. You start from a mean field state, you explore it, you map out the phase diagram. But you need the adiabatic state preparation, which time evolves to prepare the ground state or a good guess for it. And you need the phase estimation to really project onto an eigenstate, and both need time evolution. That was okay? Yeah.
I was wondering, so, like, with the 4 algorithms we have in quantum,
yeah,
but we have no idea, I guess, that that's an exhaustive list. But
no.
How much research is done, or how likely do you think it is that this list will be expanded a lot, given that the quantum computer is there and people start tinkering with it?
Yeah, well, that's the hope, but I think we can also have you think about it now, just with that quantum computer coming, start thinking now. But I wanted you to get a feeling for which problems might be suitable or not. When it's big data you have to load in, it's hard to get a speed up. Or when there's lower bound that the classical code also matches, like with weather predictions, because it's linear in mesh size and time, then maybe that's not the best. Good problems are ones where you have little input data, little output, and lots of compute in the middle. Then we also saw that maybe nonlinear problems are hard because quantum mechanics is linear, so maybe linear problems could be good ones. Or problems for finding structure could be suitable ones, because that's what nature can do well. So just think about what can quantum mechanics do well? What can nature do well? What is a natural fit? But you can also think much broader. For example, where did classical computing really take off? It took off with games and social networks. can you think of quantum games? If you can invent a game that every teenager in the world wants to play it, but it needs quantum hardware, there's an application. Or right now, on Facebook, you can have friends, but you cannot be entangled with your friends. If you really find it that you want to be entangled with your friends, if you can make that important, can you define some quantum social network that adds value? You see, you cannot be entangled with 1,000 different friends, so it makes you choose which other qubit yours should be entangled with. You can have quantum wedding bands where I'm entangled with my wife. These could be applications, just to make you think broadly. Think outside the box and come up with something. Or it could ultimately be most useful for quantum sensing, if you can really find things in the body much more precisely with a quantum sensor that I then evaluate with a quantum circuit afterwards. That could be an application. Let's think of new applications. New quantum algorithms that are really new concepts come about once a decade. There's Grover search and Schroeder factoring and linear system attempts algorithm. They're all based on the same principle, but and phase estimation. So we worked for about 30 years on quantum algorithms. We have about 4 or 5 fundamental algorithms. It's hard to find new ones, but we have to find more. If we don't find more, is it a problem? I mean, all of our modern technology is based on progress in material science, on new materials. If we build a machine that really lets us accelerate the discovery of new materials, I think that could really be enough to make it worthwhile. But that's why I want to focus for the next few years on the chemistry problems, catalysis mostly. And of course the quantum science problems. Optimization we're doing already on classical hardware. Cryptanalysis, I think we need to know when it's possible so that then we start switching to other encryption schemes. Of course, jokingly, if I had a quantum computer, a big one now, with a few thousand fast qubits, and it could break the Bitcoin encryption, then there might be a short-term opportunity there. And that could maybe repay us for the cost we had. But at the moment people realize that you can steal Bitcoin, it's over. I think before we do that, people will switch to quantum safe Bitcoin. So again, that's not an application that will be valuable. The value applications will be in chemistry, material science, catalysis. Let's just say we use a quantum computer to help design a catalyst for carbon fixation. We can take carbon out of the air. That alone would make it totally worthwhile to build a quantum computer. Or just being able to use it for that makes it worthwhile. Right? We don't need to more reason to build it.
But also for these problems such as catalysis,
yeah,
It sounds to me like you need to have a pretty good starting point if you are going to use a quantum computer to optimize those problems, right? Because what you can gain is correlations in the deep orbitals.
Yes.
So you need to...
So for catalysis, we already know how to simulate it classically. We can find all of the transition states because kind of the structure and the minima, that's pretty well done with DFT methods. But to understand the reaction mechanism, I need to know which barrier is lower. So I need to have really precise values for the energy differences, for the barrier heights. And if these are metal-based catalysts, then correlation effects are important. And we don't have the classical methods that are good enough. That's where the quantum computer will help to solve that sub-part of the problem. We still need the big classical calculation around it. We just make it more accurate so that it becomes more predictive. Yes, we need the good starting point. We need all of the classical world. This just improves some of the hard problems. Thank you.